All right, so continuing with today's lecture, we're going to continue talking about Newton's laws of motion, but we're now going to start applying things. In the last lecture, I talked about free body diagrams a lot. It was kind of a quick overview. Hopefully you have read through the notes, or at least begun to. And we're probably a little bit confused by that, and it's a little tricky. So what we're going to do today is one problem. That's it. I'm going to lecture on one problem. It's probably going to take us the whole class period to do because I'm going to step through it very slowly. The reason I'm going to do that is because you're going to need to go back and rewatch this lecture. I can almost assure you that you're not going to get this the first time through. That's okay. That is perfectly normal. This is one of the first kind of big hurdles in intro physics. And this is probably the first time that you've actually had to do anything meaningful with it. This is what I call big boy physics. So let's begin with a problem setup. See, is that legible to you guys on the whiteboard?
Yeah, I can see it.
Okay.
I forget about the speaker.
Yeah. Okay. So this is a problem that you typically see called the inclined plane problem. If you need examples for how to do this kind of problem, go do a Google search for inclined plane problems, and you will get hundreds and hundreds of pages and YouTube videos of variations on this problem. They're all going to solve the same way. So in this inclined plane problem, let's say that what we want to solve for is the acceleration of this block. So just to describe what I've drawn here. Here I have some sort of ring. It makes some angle theta with the horizontal. And there's some kind of block of mass M that sits on this ring. I'm going to make some assumptions. We're going to assume that we're on Earth, and we're going to assume that there is no friction. Okay, in other words, there's nothing preventing the box from sliding. It's not rolling. There's no air resistance. So we're going to take all that out of the equation. We're going to assume theta is a constant, as is the mass of the block. In other words, the ramp does not change angle over time, and the block does not gain or lose mass as it slides down the hill. I'll talk about later how you might approach that if those things were true, but I'm certainly not going to expect you to solve that problem because the problem of changing theta and changing mass is a graduate level course called classical mechanics. And we're not there yet. This is very fascinating. So this is a typical inclined plane problem. Remember what we want to solve for. We're going to say find the acceleration of the box down the hill. This is all we have to go on. But we're going to be able to solve this pretty easily. The first thing we want to do whenever we solve a problem like this is we need to pick a coordinate system. Remember, physicists are lazy. I am going to pick a coordinate system that makes sense for the problem. Now, the reason I emphasize this is because you may be tempted to say, this is positive y, and this is positive x. Don't do that. If you do this, this is going to cause you pain. It's going to cause you more pain than you need on this problem. Why is that? Well, the reason is because the motion that we want to measure is this acceleration. I've given you a clue here, and you've kind of already intrinsically thought about a coordinate system by writing the problem this way. I want to find the acceleration of the box down the hill. So I've decided that downhill is along this slope. So that's really what my coordinate system is. So don't do this. Instead, let's pick a different coordinate system. Let's pick a coordinate system with its origin on the box. The positive direction will be the direction this thing's moving. Our up in relation to that box is positive. Our down in relation to the box is negative. And going backwards would be our negative direction. This more accurately shows the problem we're trying to solve, the acceleration of rocks down the hill. This is going to make your life way, way easier. So we're going to have to do a couple of things. The first thing that we want to do here is we want to start defining some things. We need to find out what we know. Well, the first thing that we're going to notice that makes this problem complex is this angle theta. If this was just a flat surface, and I wanted to find the acceleration of that box, go to different whiteboard here and draw that problem. Imagine this. Here's your box. Here's your box on a flat ground. If I do nothing to this box, what is its acceleration to the right? It's got to be 0. Why? Well, because this is a flat surface, right? I'm not touching the box. Nothing, no force is being applied. Remember, Newton's second law of motion tells us that the acceleration is directly proportional to the mass of an object and inversely proportional to the amount of force applied. In other words, if there is no force, if force is 0, in order to make this equation balance, then you have MA, one of those has to be 0 in order to make force go to 0. Well, if the mass is 0, then what's the point? So that means there can be no acceleration if there is no force. I'm not pushing on this box at all. Now, if I make force positive, if I apply some force, then yeah, I'm certainly going to get an acceleration. That box is definitely going to move. How fast is it going to move? I don't know, it depends on how much force I apply. So this is an easy case to solve. If we want to know what the acceleration of this box is to the right, then what we're really going to have to do is just add up the forces. This is a thing you might not have noticed about Newton's second law. F equals ma. F is the total force. M is the total mass and A is the total acceleration. So more accurately, what we're looking at is the sum of the forces, is the mass times the acceleration. So I got to come up with what forces are acting on this box. Here's where we need our free body diagram. So let's draw a free body diagram with the mass at the origin. And here. And let's pick a direction. Let's pick our positive X. We'll call that negative Y. So let's just look at positive X. What forces are in the positive X direction? This applied force. So we can say, we can make a table. Our forces in the X direction. Certainly the directional force F. That's our applied force. In fact, I'll label that S of A for applied. Nothing else is acting in the F direction, in the X direction. There's nothing negative acting, there's nothing positive acting. The Y direction is a little different. We have to think about this. There are actually two forces acting in the Y direction. The one that is obvious to you, or should be obvious to you, is going to be the weight. Now, in this case, we're looking at weight. Weight is a force. Remember, I talked about that last time. So the force we want is the weight. It is equal to the mass, it's a force, so all forces are ma. The mass of the object, m, and the acceleration of the object in the Y direction. So what is causing the box, if anything, to accelerate in the Y direction? The negative Y direction, that's our gravity, right? So that's our acceleration due to gravity. So our force is W equals mg. Newton's second law lets me do this pretty easily. However, if this is the only force acting on the object, notice I have not said anything about what this surface is. This might be concrete. This might be paper. Might just be a cushion of air, right? It's just some boundary that I assume and something that the box is resting on. If the only force that is present is the weight force, there's nothing that stops this box from falling. So there has to be a force that balances it. Newton's third law tells me that every applied force has an opposing force in the opposite direction. Many times you'll hear this as every action has an opposite reaction, a simplification of the rule. But think about it in terms of forces. There's some force pulling this box down. Well, if there's a force pulling the box down, since it's not accelerating towards the center, there must be another force that is its equal, but in the opposite direction. So if this force is mg, then there must be another force that's the same magnitude, mg, but in the opposite direction. So we use negative to indicate our opposite direction because we just kind of said, well, that's positive. This is what we call the normal force. So notice, now we go back over here to our chart and we list the forces that exist in the y direction. So in the y direction, we have this normal force and we have the weight. We've now listed all of the forces that are acting on this box. So let's do this first. Let's add all of the forces in the y direction. Well, that's our normal force plus our weight force. We know the normal force is minus mg. We know the weight force is just mg. So minus mg plus positive mg, it's got to be 0. So that means there are no net forces in the y direction. Remember from our basic examination of Newton's second law, if there is no net force, then there can be no acceleration. If there is no acceleration, there is no change in velocity, because we know the definition of acceleration. If there's no change in velocity, then there ain't no change in position. So this thing's not moving in the y direction. But what about the x direction? Yes, there is a normal force to the applied force. It's the force of the box pushing back on me as I push forward on the box. The box is not going to move me. My mass is much, much larger than the box. So those two are going to cancel each other. However, we've still got to account for this force in this direction causing this acceleration. So our forces in the x direction are that applied force. That's it. So then that means through Newton's second law that the applied force must be the mass times the acceleration. And if we want to know what the acceleration is, we just solve this algebraically. Acceleration is just F sub A over m, or newtons per meter, or newtons per kilogram, sorry. That seems a weird unit for acceleration. Let's look at it. It's force per mass. That's what we just came out with. Force is measured in newtons. Mass is measured in kilograms. Okay. So you're telling me that acceleration is Newton per kilogram. That still seems weird. That's not what I taught you a couple of weeks ago. I taught you that acceleration is change in velocity over time. But I did teach you that there's a unit called a Newton. The Newton, remember, is a kilogram meter per second squared. So that's our Newton. So Newton's is kilogram meter per second squared. We still got a kilogram down here. So kilogram meter per second squared per kilogram is where we're at. That's a messy unit. But if we remember algebra, our kilograms cancel. And this works out to be meters per second squared, which is our formal and our kind of normal definition of acceleration. So when you solve this and you find acceleration is force per mass, that makes sense. Newtons per kilogram is an acceleration. You're probably noticing as we go through these problems that a lot of times you're going to encounter different measurements that have units that may not be consistent. Sometimes we'll use meters per second, but sometimes I'll call that a velocity. Forces are measured in newtons, but really force is kilogram meter per second squared, which is a messy unit to work with, so I just call it a newton. The point is, if you understand how to do unit conversion and you understand how to do dimensional analysis, then you can find easily that this is true. The reason I tell you this is because you may encounter problems where you are given all this in mixed units. You may be given a force in pounds. You may be given a mass in, I don't know, seashells. And I could make up some unit conversion for seashells. One seashell is 0.25 ounces or something. And you can see how that would get messy. But my point is, if the units are not the same standard, the one we use in physics all the time is the SI unit. So if we're not talking about meters and kilograms, then the first thing you need to do is convert. Because if you don't, none of this is going to work. Because a Newton is defined as a kilogram meter per second squared and not something like a slug foot per feet or something. Slug foot per second squared, I guess, or slug foot per minute squared. Nothing weird like that. So you have to do unit conversion. But that is how you're going to solve all of these problems. Just like this. That's not too complicated, I don't think. The easiest thing for you to do when you solve these problems is make this little table. Make a note of your X and your Y forces. You've seen this notation before where I have X sub X and F sub Y. You've seen that in the last unit where we were talking about two-dimensional motion and we needed an X component of the velocity and a Y component of the velocity for doing the cannonball problem. Well, same notation, X component, Y component. Whenever you see something that uses X component and Y component, now guess what that means? That means you're going to have to use some trig. You're starting to see why I did that lecture a couple of weeks ago about reviewing trig, because it's about to become really important. So let's go back to our inclined plane problem. So here we've got our inclined plane, some angle theta, a box of mass m. We're assuming we're on Earth, so our acceleration due to gravity is g. We don't have any frictional forces stopping this thing from sliding, and we're assuming that mass and the angle are constant. Nothing's changing the angle of the ramp, the box is not losing mass. We want to find the acceleration of the box down the hill. So let's, first of all, we've worked out what our coordinate system should be. So remember my checklist from week 1. I've drawn a picture, or at least I've started to. But I still have a little bit of a problem. Still have to label some things. We know that our gravity acts that way. So we've got some force due to gravity going straight down like that. We know there's a normal force. That's the force that's pushing the ramp, pushing against the box, that has to equal whatever that force is. And we know those two have to be the same. Otherwise, that box would be bouncing around. So we're going to call that the force of the box for now. We now know if this is gravity, and gravity is not acting directly along the line of our motion, it's not acting directly along our vector here that we set up. That means that some of the gravity acts in the x direction and some of it acts in the y direction. So let's try to use a different color. So this is going to be our force due to gravity in the y direction. And this is going to be our force due to gravity in the x direction. Well, let's do some solving here. What is the force due to gravity? Remember, gravity itself is just an acceleration. The force due to gravity is just the weight of this box. So Newton tells me that F equals ma. Any force is mass times acceleration. What I want is force due to gravity. The weight. That's just mg. So that's this. Well, cool. But how do I account for this theta? Well, think about this. What works out is, if you notice that we are going to have a really nice right triangle problem. Right here. Here's our right angle. Here's our theta. We know the side that is opposite of the angle. Oh, look where I'm going with this. I need to know this, right? I need to know FGX. That's going to give me the force due to gravity in the x direction. Remember how we handle this. If we want something in the x direction, well, we look at what we're trying to find. We know an angle. We know the opposite side. And we know the positive side. Good. All right. What trig function do we need? Well, we need something that has opposite and hypotenuse. So that looks like sine to me. So that means that we can say FG in the x direction is going to be sine theta of FG. But FG, I know, is just mg. Cool. Well, that means that through the same logic, that F sub G in the Y direction, this, I should probably write that in green, that's what I labeled it. Is that. We also know that this normal force has got to be the opposite of whatever this box force is, which is FGY. So that's going to be negative of FG sub Y. Cool. So now we can make our table. Our F of X and our F of Y. Remember, we know we've labeled X and Y in line with our motion. So let's just start with the X direction. Remember, our X direction is in the direction of the hill. So our F direction here, that is force of gravity in the X direction. And nothing else, right? I'm not applying any force. There's no frictional force. None of that. In the Y direction, it's a little more complicated, but not much. In the Y direction, we have this normal force here. You know what? I'm going to try to stay consistent with my colors so that when you go back to read this, it's a little easier. In my Y direction, I have the normal force. And I have FG sub Y, which is just something I call the box force. That's it. That's all of the forces that are acting on this box. So now, knowing Newton's second law means the sum of all the forces is equal to the mass and the acceleration of the whole system. Over here, I can say F in the X direction. So my forces in the X direction are the sum of all the forces in the X direction, Fg sub X. And my forces in the Y direction are my Fg sub Y plus the normal force. One of those is negative, right? Because of our directions, we'll just put it on the normal force. Doesn't really matter because we know those are going to go to zero, which is really excellent because I know this thing's not moving in the Y direction, right? It's not oscillating up and down like this as it goes down the hill. Now, I can absolutely do that problem, but again, that is a graduate level classical mechanics problem that you guys are not ready for and won't be for several years. But it is really fascinating. So the only forces that I need to worry about are this F sub X. So I've summed all the forces in the X direction. That's my Fg sub X. Well, what does Fg sub X look like? It looks like sine theta mg. I know because Newton's second law tells me that has to be ma. Well, look what happened. The masses go away. And what I'm left with is sine theta of the acceleration due to gravity is the total acceleration of the system. This is what I'm trying to find. Well, what happens if you don't do it this way, and you just start plugging numbers in, and you have something that's mg, I'd give you the mass numerically in this thing, and you'd know the acceleration due to gravity. And you'd have a mass over here, and you'd have an A, it's still going to work out. All the things are going to cancel, you need to cancel. So in this case, in the absence of friction, our acceleration is only dependent on the acceleration due to gravity and the angle of the hill. Very cool. Notice something that we did here. I did not put any numbers in this. You guys are all worried on the exams and on the homeworks about numbers. And what a lot of my physics students try to do early on, even high school students are really bad at this, is you just want to plug numbers into a formula and go. If you do that with this kind of problem, you're going to be in a world of hurt. So, what you do is solve this symbolically. And that's what we've done here. Every physics problem that you ever need to do, while this may look painful, your life is going to be greatly simplified by solving symbolically first, then plugging numbers in. Now, what we're going to do in the next lecture is we're going to start making this more complicated. We're going to start looking at friction. We're going to worry about frictional forces, right? This thing is no longer going to be on just a sliding frictional surface or frictionless surface. This is going to be a box made out of a brick on an incline covered with sand. And so we're going to have some friction there. And I'm going to show you how to get friction and what that really means and how to apply it to this kind of problem. We're also going to do this problem a different way. We're going to push the box up the hill. Instead of letting gravity do the work and slide down the hill, we're going to figure out the box going up the hill. And if I have to push this thing, then how much force I need to exert. This is something I'm really interested in, being an old, fat, lazy dude. I don't want to do a lot of work. I don't want to push too hard on that box. So I'm going to use this incline to do the work for me. In fact, this principle of this inclined plane, this is one of the fundamental machines. You're going to hear about fundamental machines in physics. The first one that we're encountering is this. It's called the wedge. Simplest tool known to man. I had an evaluator in the Air Force that we called the wedge because he was the simplest tool that we knew. This is a wedge problem or an inclined plane problem. So, having said that, I think I have probably loaded you with a lot of knowledge today that you didn't know that you needed or wanted. You may still not want it, but you have it. There it is. Again, I know this is complicated. Go back and watch this again. Come talk to me in my office when you get stuck, because you will. We'll talk about it and move through this. But this is a critical piece of physics. This is why I did not include this on the first exam, because you're still trying to figure out vectors at this point, and I didn't want you to have to fight with that and then try to apply it like this. We'll be on the next exam. Speaking of the exam, as I said, I sent an email this morning. The next exam will be on Friday. It should become available to you at 8 in the morning on Friday on WebAssign. It's not too bad. It's 10 questions. I took them directly from the homeworks. So if you've been doing the homeworks, you're going to have seen these problems before. Don't think you can just go back and look at the homework though and plug in your answer from there, because the number's going to change. They have to actually calculate directly. But the problems themselves come directly from the homework. It's going to go live on Friday. It is not timed. You just have one chance to put the right answer in. And it will be open for you until midnight on Sunday. I know a lot of you have other commitments, and I wanted to give you the maximum amount of time to work on this. You may use your notes, internet resources, whatever you need to use, to solve the problems, other than getting together with everybody else in the class and going, hey, how do you do this? Well, the reason I like to do that is because in the real world, when we're solving problems as physicists, mathematicians, and scientists, I don't think we memorize all this. Yeah, we gotta look it up. If I don't remember what these formulas are, I'm gonna look them up. It's the application that I want you to get at. It's the using these vectors and using the idea of summation of forces that I want you to do. So that is all I have for today. And so I will see you guys, I guess Monday. And like I said, don't forget to do the exam.